Hi everyone. It's working. Yeah. Okay. Oh, hi everyone. It's great to see so many familiar faces and a wonderful reconnect. My name is David Tóta. I'm from Hungary, and I work at the AdGuard in the extensions team. I'm delighted to welcome everyone once again to the Air Filtering Summit here in the beautiful city Berlin. Last year, I had the opportunity to present AGTree. This time, I'm excited to dive deeper and share the latest developments of AGTree, the powerful parser that drives it forward. My presentation will be quite technical, but I try to do my best to explain things a way that highlights the key points for everyone. Also, apologize, my English is still not perfect, so I will be reading a lot of from my notes. Well, my presentation covered three main areas. I will start by looking at AGTree in a nutshell to give context to everyone. What is AGTree? Then I will explore the exciting new features that have recently been introduced. Finally, I will see how AGTree is powering new software solutions to streamline and optimize filter management. So AGTree in a nutshell. What is AGTree? It was originally just a parser. So simply take a filter list, take a filter rule, parse it to AST, and there was a possibility to generate string back from the AST. And that's it. Now it's a universal tool for working with filter lists. So we added a lot of features next to parsing. So as I told you, initially there was parse and generate. Basically, for technical people, of course, it's not new, but we have some raw string like a filter list, and we pass it to the parser, and it's produce an abstract simple string, AST, so-called AST. And on demand, you maybe want to generate raw string back from the AST, and basically, the generated text doesn't always match with the original rule text. It's because AST typically doesn't store formatting related information. However, there is an option in AGTree to store the original filter list in a property in the AST, and in this case, AGTree just reads this property. And restoring the original filter list is possible for filtering rule. Yeah, basically, AST is just a compact structure to represent information or by the rule, and many contexts can be parsed. For example, what I said, a filter is filtering the rule, but we have a component way in AGTree, so it is possible to parse a modifier list, a domain list, on regular expressions, network rule patterns, so there is a lot of features. And yeah, generating string from AST. Sometimes we want to get the string. It's the typical use case when you parse the rule, doing some modification on AST, and after that, you want to generate it to string back. It's also can be used for formatting purposes. It's a future plan to add some formatting notions to generate. I don't know, for example, cool type of scriptlets or something like that. But an important thing, the naming of the rule remains, even if formatting is different. And on the screen, you can see an example of what an AST node looks like. As you can see, even a simple network rule provides a lot of detailed information. So it's one of the most simplest rule that can be parsed. And the parsing detail can be changed. So for example, you can also include location data as a source mapping. It's useful when you, for example, want to underline even in toolbars in an editor, for example. And I made a very simple playground page based on AST Explorer project. And if possible, I want to show you. So here you can see on the left panel, there is the raw view tables. And in the right panel, it's the bars AST. It's quite straightforward, so you can see the row types. And if you hover, for example, this one, you can see it's highlighted on the left side. And it's quite detailed. For example, if you go to the comment one, and you can see there is a marker is highlighted if you see for the comment text. And yeah, we have a lot of row types. And also, you can change AGTree version here. We have two main versions currently, and you also can enable a so-called transformation. It can be in code. Basically, my example is just a converting. So in this case, here you can see the transformation mechanism, and here you can see the result. And basically, it's just a conversion to AdGuard syntax. Maybe I can scroll down a bit, and yeah. For example, here you can see it's a UBlock syntax. And if I scroll down in the result list, you can see all of it fits in AdGuard syntax. So basically, this is this small demo page. Turn back to slides. Now it's time to talk about the new AGTree features. It's just an introduction for AGTree. So, we added these new features: compatibility tables, rule conversion or filter list conversion, validator, and serialization, deserialization, and some small helper utilities. Well, first is compatibility table. It's cover a specific part of the syntax, including modifiers, scriptlet names, and redirect resources. We also plan to expand it later with extended CSS pseudo classes. But currently, you can imagine it's like this. So basically, every type of entities, like in this case, modifiers, has a role, and the columns are the platforms. To categorize efficiently, we needed to define the platforms. And we have three main platforms, which is naturally came from AdBlockers itself. And the platforms they should support. And in a bit detailed version, we need to distinguish between two main platform types. The first is the specific platform, such as AdGuard for Windows. It's quite specific. But in many cases, we don't need such a strict specific categorization. So a more general category is, for example, if I want to talk about just for any AdGuard browser extension on any AdGuard product, including content blockers or OS-wide tools. It's the general platform, which is basically a union of specific ones. And it's used in the compatibility table. Basically, it's based on the specific platforms that you can generalize. And the compatibility table essentially, as I know, store data by row by row, and columns are representing by special columns, buffers, sorry. And here you can see what type of fields are stored. For example, in general, basically we always store the entity name, short description, documentation link, but some specific compatibility tables has additional fields like scriptlets, for example, parameters. And for better maintaining, we store compatibility table data in YAML files, as shown in the example on the right side. Each file, such YAML file, represents a row, and keys are the columns. So you can see AdGuard any, AdGuard plus any, and corresponding data values. And deep technical part, let's take a look at few programmatic examples how to interact with the compatibility table API. A common use case might be checking if some particular modifier exists or not. So you just import modifier compatibility table, then you call exist any, and third-party, and it returns you to if it matches with any platform. And you can do it more strictly. So if you are interested, for example, if third party is supported by any AdGuard Plus product, or you can use a header function parse row platforms, and it's basically parse the syntax from the YAML files. Because in the YAML files we have a small syntax, you can combine the platforms. Well, and if you want to get some data set for a specific platform, you can do it. So for example, if you are interested in third party, you just call get single, specify the name. It's always based on the name, and you give the platform, and it returns you the data from the YAML files. And challenges. While implementing compatibility tables, we encountered some interesting challenges. In some cases, compatibility is more complex than just a difference between names or values. For instance, there is third-party and not first-party case where the compatibility is defined by negation. Similarly, the legacy MP4 modifier can be represented by two other modifiers. So these are a bit more complex relations, but actually we don't handle these cases yet. But even so, the compatibility tables address most of the essential use cases. And the last side about compatibility tables, there is another important challenge with compatibility tables, keeping them up to date. So I'd like to take this opportunity and invite our amazing community to collaborate and help implement the compatibility tables used in the linter, VS Code plugin, and tools that support the everyday work of all filter maintainers. To make things easier, we set a separate repository for compatibility tables data, and we will be migrating everything there soon to simplify maintenance. Yeah. And next topic is converter. Converter's role is transform an entire filter list or just a single filtering rule from one syntax to another syntax if possible. The Converter API primarily works with AST nodes, converting from AST to BAST practically. However, since a common use case involves converting from string to string, so we implemented a wrapper around it to support this string-to-string conversion as well, efficiently hiding the boilerplate code needed for parsing and generating. But it's still a AST to AST conversion under the hood. And let's take a look at API. It's quite simple, providing three methods: convert, AdGuard, AdBlock+, and figure. Conversion result is an object, always with two properties. First property is just a flag indicating whether a conversion took place. And the second is the result itself. And if no conversion happened, the original AST node reference is returned in this result because of performance reasons. Because in this case, we don't need to do a cloning, because deep cloning can cause a lot of performance problems. And this slide is also quite technical, shows a minimal working example demonstrating how to use the base converter API. So there is a rule. It's just a simple rule. You pass the rule, pass it to converter, the rule node, and then you console conversion result.map, and you map it with the generate function. And its result you the converted rules. It's two converted rules in the result. It's an interesting case because only AdBlock+ allows using multiple snippets in found rule. And this slide shows the same example by functionality, but it's using the string-to-string wrapper. So you can see the row rule converter, and its returns you the same result. So if you want to do a string-to-string conversion, you don't need a lot of boilerplate code. And of course, it's also possible to convert the whole filter list. The simplest approach is just read the file content, doing the conversion, and write it back to a file. So actually, that happens here, and it converts filter to filter AdGuard TXT. And there are some conversion errors if something prevents the conversion, like syntax problems in HTML filters or modifier problems. But it's limited. So most of times converter performs the conversion, and I will take a deeper look of rows a bit later. An interesting case that I showed in the example, a single rule can be converted into multiple rules, because, for example, AdBlock+ supports multiple scriptlets. And the future plans in the converter, basically, currently the converter implementation is not fully complete. It supports AdBlock+ to AdGuard and uBlock to AdGuard conversions, as well as a limited form of AdGuard to uBlock conversion. However, we plan to expand this to fully implement conversions across all of the syntaxes. Another potential development in the future is to make the conversion even smarter by merging N rules, so some rules, from the original filtered list to N rules in the converted filtered list. It's a more complex relation, some cases, but currently we only support one to N conversion from the original filters. So it's a very future plan, I guess. The next topic, and these are connected actually, so validator. Validator is responsible for checking filter rules, ensuring everything from domains to modifiers, and essentially any element within a rule is validated. However, the validator API is still in its early stages, so I just briefly mention it here. We plan to integrate it more fully in the future, such as within the linter, for example, and it has a great potential for use in the other areas as well. And I believe it's important to take a look on the distinct roles involved in validation to give the audience a better understanding of intentions behind each stage. The parser, for instance, only flags syntax errors. It will parse a rule that may contain invalid elements, such as incorrect domains, non-existent modifiers, or unsupported scriptlets without an issue. And it's intentional. So the parser's goal is to create the most detailed AST possible with the minimal validation, leaving deeper validation for later stages. So if needed. So it's a bit lazy way. Similarly, the converter also isn't a fully validator. Converter only throws error if something blocks the conversion. It cannot be resolved. And that's why I mentioned before. Finally, of course, the validator's role is to perform the full validation, checking all aspects of the rule. Yeah. And next topic is serializer and deserializer. The idea for the node serializer came from our need for a solution that could help us to avoid reversing while keeping storage usage efficient. Finding this balance was a bit challenging, especially given the significant performance differences between platforms. So, since everybody loves the numbers, I share some specific data to illustrate the kind of results we achieve with this implementation and how this compared to other approaches. So, for example, when we parse of EasyList with AGTree, EasyList itself is 2 megabytes. AST JSON object is a bit too larger. And if you serialize it with binary JSON, it's a common use library in MongoDB, for example, it's almost the same size. So it's not for us. Also, JSON stringify has a large size, but our serialized filter list, which hold every necessary information too, is only 5.5 megabytes. And the next one is the speed, because size is just 20. So parsing EasyList is 60 milliseconds. Deserialize with JSON parse is more than parsing. So actually it works pretty well. Deserialize from binary JSON is much more than parsing, and then using a lot of memory, of course. And deserialize from our binary data is just 30 seconds. Yeah, essentially we work, so I'm talking about a bit what happens under the hood. So we work with 3 main buffers. The core buffer is byte buffer class, which wraps around uint array and allows the buffer size to expand dynamically using chunks. It operates quite simply, just a read and write method, and that's it. So it just gives you a dynamic buffer. But we have 2 helpers, output byte buffer and input byte buffer, which are wrappers around byte buffer, each containing an internal cursor to keep track of the current position in read or write operations. And also have helper functions, for example, writing integers, writing floats, writing strings, reading strings, because byte buffer is just a byte level thing. But output byte buffer and input byte buffer has helper methods for every data structure they need. Yeah, and here is how its API looks like. Basically, serialized waits for a node. It's the AST node, a buffer. During serializing, it's an output byte buffer, and some additional arguments if needed. It's very rare case. And deserialize, it's the same. It's waits for the buffer and the target node, where it writes data deserialized from the buffer, and also some additional arguments. And via serialize and deserialize, the internal cursors are incremented in input byte buffer and output byte buffer. So we don't need to do it manually, helper functions do it. So we just read and write, and if needed, we can change the position of the cursor. And we write the data to the buffer in the following way. So first, we just write some indicator. It specifies the data type followed by the data itself. Certain data entries are designated with a null character to sign feed and like you see. We try to reduce unnecessary null terminators to save storage space. So in obvious cases, we just skip it. And as you might expect, compatibility is important. So scheme changes can happen, and previous schemes may no longer be deserializable. To prevent this problem, we reserve the first 4 bytes of the byte buffer for the shell version. And if there is a null compatibility, the deserializer automatically refuses deserializing the incompatible byte buffer. And there was some serious challenges during implementing the serializer. 2 main issues. The first was the native text encoder and text decoder, as strong, short, high marshalling times for many small strings. To address this, we implemented a custom polyfill based on specs for Chrome, where it performs better for small strings. So the native encoder and decoder works well for large strings. So if you encode or decode the whole easy list, for example, it happens within milliseconds. But if you split it to lines and try it line by line, it performs much worse. So it caused the 2-time slowdown in the deserializer, so needed to polyfill. And there are some open issues even for Node.js about this program. And the second challenge was handling so-called frequent values, such as numerous modifier or scriptlet names. So instead of serializing and deserializing these data as strings, we assign them with a numerical code and use a map to match these codes to support non-modifier and scriptlet names. This approach, we just call frequent values, and this helps a lot optimizing storage usage. Because, for example, what I showed before, binary JSON writes everything as is. But these frequent values can help a lot. Yeah, and I'd like just weekly mention that AGTree also includes a few helper utilities. These are minimal but well-separated tools that can be useful in many situations. For example, you can get a rule category, change the whole types of scriptlets, and it also handles escapes, validating domains, working with regular expressions, or it's an interesting thing, logical expression evaluator. There are expressions in preprocessors, and you can get the variables, you can set true or false values for variable names, and it gets you the value. And the future plans for AGTree. Looking ahead, one of the most exciting potential features in a robust CLI that provides function what we discussed before, and even adds new ones such as, I don't know, checksum validation, statistics, and more on demand. So it's just possibilities, ideas. Yeah, so that's the new features in AGTree. So as you see, it's a bit more than a simple percent. And now it's time to discuss how we put these new AGTree features to practical use in other software and how they benefited us. So last year I introduced 2 of these software. The LinkedIn and VS Code plugin. In my today's presentation, I'd like to focus to other browser extension and then So let's take a look how our browser extension work before integrating AGTree. To be honest, this diagram doesn't represent the exact reality. I simplified it to make it easier to present. But that's the point. Previously, the browser extension functioned by downloading raw filter lists and just storing them in browser storage, local storage area, and then performing rule conversion and rule parsing every time on every engine initialization via scanning rules. Parsing also performed within the scriptlet library. Actually, it worked fast, but we wanted a solution that avoids a lot of reparsing. So we modified the structure a bit, and it is how it works now. So the new mechanism works as follows. When a filter list is downloaded, it's processed, and we store it as a so-called preprocessed filter list. I'll go into more detail on preprocessed filter list in the next slide. But the key point is that this filter already converted, and its associated AST has been serialized to binary format. So that's all we need. This way, no additional parsing is needed. We simply just pass the byte buffer and source back to the engine, which reads the data directly from the input byte buffer by Deserialization. And of course, we also modified all tools to expect AST nodes instead of raw strings like TS level filter, raw classes, or our scriptlet library. And reprocessing filter list is a compact structure that enables efficient storage and flexible usage of filters. Since the filtering log is one of the AdBlocker's most essential features, we need to be able to display the original rule text in the filtering log. This is somewhat complex, as the engine no longer has direct access to the original rule text like before, only the information contained in the AST, which is deserialized. So let's move to the next slide and take a closer look on preprocessed filter list. So initially, we start with a filter list, this input filter list, which may contain various types of rules such as AdBlock rules or BlockRule rules or anything. At first, we just convert this filter list to AdGuard syntax, resulting in a raw filter list now formatted for AdGuard. And it's important to have the ability to revert this converted filter list back to its original form without any loss or changes. This is where the conversion maps comes in. It maps the line start index offset of each rule in the converted filter list back to the original rule. There is two slides, is the abstract, and there is a next slide. I try to switch. So you see there is a first party rule, and I'll come over. It produces us a converted filter list because we use third party, not this syntax. And we have conversion here. So the 0 means the first rule line start index. So we have a map 0 and the original rule. And from this to data, we can restore this anytime. Additionally, we also store the line endings, so it's for a template. That's the first part. It comes naturally from the converter. And let's see how things are connected. A bit back. Additionally, we need to AST of the converted filter list, which is stored in binary format. So this serialized converted filter list is equals this, just the AST representation in binary form. And actually, somehow when we press a rule to the engine, we know the rule start index in the byte buffer. and we need to get the applied voltage, which is actually this time. So we convert the one. So first step, based on the source map and the start indexing byte buffer, we can retrieve the supply tool start index. So actually you can use the two maps together. So 0, 0, and you have the original voltage. It's a pretty complex, sorry for that. So for this again, engine gets the start index from the byte buffer and the source map, and that's it. And these other two fields are just stored in the extension because we don't need it while operating with the engine. We just need it when filtering log is open. So in essence, these two steps, we can retrieve the original voltage from the binary data on the engine. So here it's a detailed slide game. So we map start indexes using source map. And yeah. Well, for that domain thing, over the years, certain filter lists have grown too big, and it making it essential to identify outdated rules that are no longer needed. A typical example of this is a domain list that is no longer in use, so it's dead. Whether it's this, Andre developed the that domains linter, which is also built on AGTree. And I believe this is a very useful tool. So I give an overview at my end of my presentation, and I hope many of you will find it helpful as well. So how it works? Scans, you can specify a globe pattern, scans your lists, and extends domains, and checks them with AdGuard DNS, and prompts you to decide on probably the domains, because there are some false positives here. So this is why we use a prompt. Yeah. And how it finds actually the domains indicates domains that not used by AdGuard DNS in the last 24 hours. It's actually quite reliable data based on 100 millions of users. There is also a secondary DNS check, but it's not recommended for large filter lists because it has an overhead, which is double check, the first check. And why important to use it? It's actually straightforward. Keep filter is smaller, decrease the processing time, and no need to deal with outdated rules in the engine. Yeah. And future plans regarding to that domain syntax, since that domain check is relatively complex and time-consuming process. It's currently not a part of AGLint, and instead it has all minimal linking engine. In the long term, we plan to integrate it with AGLint once AGLint receives plugin support, which will create a more unified linking interface. Also, in our super secret Slack, I posted a workflow code, and you can use it in your GitHub repos. And it automatically opens you pull requests and removes that domain source. So that's it. Thank you for your attention and for joining me on this journey through the development of AGTree. Now it's time for questions, so please feel free to ask anything if you like to.